Okay. Thank you for the introduction, Ishil. So just as a motivating example, suppose that a security analyst is trying to determine whether an Android app is malicious. So we can use, it turns out we can characterize a lot of malicious behaviors by using source-to-sink taint flows. And therefore, we can help the security analyst with his job by taking an Android app, running a static taint analysis on the app, and finding a bunch of potentially malicious behaviors, which we can then use to, which the security analyst can then use to determine whether or not the app is malicious. The problem is that Android apps frequently rely heavily on the Android framework. And for a number of reasons, Android framework code tends to be very challenging to statically analyze. For example, native code and reflection can both introduce unsoundness since they're typically omitted by many static analyses, and things like deep call hierarchies can be very challenging to analyze precisely, and especially for things like static PointsTo analysis, and can introduce imprecision into the taint analysis. So a standard approach is to actually omit analyzing the Android framework code and instead analyze specifications that summarize the Android framework code. Typically, these specifications have to be written by hand by the human using the tool. So this can be a very costly process for many reasons. Most importantly, there are just tens of thousands of framework methods that need specifications, but also every time Google updates the Android framework, the specifications need to be updated as well. In this talk, I'm going to propose an algorithm that automatically infers specifications for library codes. And in particular, I'm going to focus on PointsTo specifications, both because PointsTo analysis really lies at the heart of our taint analysis, but also because PointsTo specifications are among the most common and complex specifications in our system. So first, I'm just going to give some background on the PointsTo analysis we use. For the purposes of this talk, I'm going to use a Steensgaard analysis. But in our paper, we describe how to apply these ideas to a context-sensitive variant of an Anderson-style PointsTo analysis. So I'm going to describe our analysis just by giving an example program on the left-hand side. And on the right-hand side, I'm going to show a graphical representation of how our PointsTo analysis works. So first, this program is going to construct a new object called val. And then it's going to store this value in a box by calling the library function box.set. And on the right-hand side, the variables in this graphical depiction correspond to, the vertices in this graphical depiction correspond to variables in the program and the library. And the unlabeled edges correspond to assignment operations. And there are also labeled edges describing field loads and stores. So coming back to the program, it's next going to create an alias of the box. And finally, it's going to load a value out of the alias for the box by calling the library function box.get. And so it's clear from this program that val and val alias may be aliased. And next, I'm going to describe how our PointsTo analysis can discover this fact when it's analyzing both the program and the library code. So in particular, our static PointsTo analysis is defined by a set of inference rules, which I'm going to show at the bottom here. So the first rule says that every variable is aliased with itself. The second rule just says that aliasing composes with itself. The third rule, also straightforward, says that aliasing composes with assignment. And that allows us to find the aliasing between box and box alias. The fourth rule is going to say that aliasing also composes with backwards assignment. So this is because we're using a Steensgaard analysis. And this rule lets us find the aliasing between the receiver of set and the receiver of get. And finally, the last rule tells us how to handle field loads and stores. In particular, if there's a sequence of a store operation followed by an aliasing relationship followed by a load operation out of the same field as the store, then the variable stored may be aliased with the loaded variable. So in particular, in our program, this allows us to conclude that the parameter of set may be aliased with the return value of get. And once we have this aliasing edge, we can go back and use the previous rules to conclude that val and val alias may be aliased. So that was the PointsTo analysis when the library code is available. But as I said before, for a number of reasons, we want to omit analyzing the library code. And in this setting, we can still see the variables in the library interface because these variables appear in the program. What's missing are the relationships between these variables. So when we run our PointsTo analysis without specifications, we can still deduce that box and box alias are aliased, and similarly that the receiver of set and the receiver of get are aliased, but then we get stuck. So what we need are specifications that summarize the behavior of the library code. So next I'm going to talk about our specification language, which we call path specifications. And I want to, and path specifications were really designed to be easy to infer. So they look somewhat different than more standard specification languages. And yeah, so I'm just going to dive in and start off by giving some intuition into where path specifications come from. So just recall that the aliasing edge we basically want to compute is the aliasing edge between the parameter of set and the return value of get. And also recall that when the library code was available, this aliasing edge was produced by this path through the program code and the library code. And basically in this path, you'll notice that the variables in this path are variables in the library interface. And the edges in this path are edges in the library. Oh, sorry, the dashed edges in this path are edges in the library. So these are the edges that we no longer observe because we omitted the library code. And finally, the solid edge is the edge in the program, which we still observe. And all right, so a standard way of specifying what happens in the library might be to say, look, there's a store edge in the set function, and there's a load operation in the get function. And with these two edges, we can find the aliasing relationship as before. But path specifications kind of turn this logic on its head. So instead, it's basically going to say that instead of concretely specifying what edges are in the library, it's going to talk about what the effects of those edges are. And basically, a path specification is going to say that if the solid edge, this alias edge, is in the program, appears in the program, then the edges in the library, whatever they may be, they complete the solid edges into a path that produces an alias edge. Okay, so that's really the key intuition behind path specifications. And syntactically, this is an example of the path specification for the box class. And as you can see, so there's a solid aliasing edge, and it doesn't say anything about what the edges in the library are. And the semantics is basically just an inference rule. It says that if you observe that the receiver of set and the receiver of get are aliased, then you can conclude that the parameter of set and the return value of get are also aliased. So if we add this inference rule to our PointsTo analysis, then we can discover the aliasing edge we wanted to find. And then we can use the remaining rules I described earlier to discover that val and val alias may be aliased. So there's one simplification we can make. So we prove a theorem in our paper, which basically, this is just a kind of hand-wavy statement, but it says that it suffices to use path specifications where all of the solid edges are alias edges. And that means that we can basically drop the alias edges from our syntax. So then syntactically speaking, a path specification is just a sequence of library interface variables. So there are additional edges here, but those are just for intuition and don't impact the semantics. And the semantics of the path specification is as before. So it's this new inference rule. And that was just an example, but it basically generalizes straightforwardly to much longer paths through the program and library code. And the semantics are basically the same. You just get a bunch more solid edges that appear in the premise of the inference rule. So that's the definition of path specifications. Before I continue to our inference algorithm, I have to describe there's one small issue I have to describe with path specifications. And this issue kind of arises from the following very high-level intuition about path specifications. And this intuition says that basically a single path specification roughly has the following semantics. It says that if a sequence of calls to library functions appears in the program, where the parameters and return values are wired maybe in some special way, then this implies an aliasing relationship will appear in the program. And the issue is that we actually are going to need a different path specification for every possible sequence of library function calls that may occur in the program. So just to make this concrete, let's come back to our example of the box class, but let's suppose that we add a clone function to this class. Then to soundly and precisely model the behavior of the box class, we still need the path specification as before, which basically covers the call to set followed by a call to get. But we can also insert a call to the clone function in between the call to set and the call to get. And basically, to handle this clone function, we need a new path specification with edges and variables describing how to handle the behavior of the clone function. And we can just insert another call to the clone function, and now we need another pair of variables and edges. And in general, we can have an arbitrary number of calls to the clone function, so we're going to actually need an infinite set of path specifications to soundly and precisely model the box class. And actually, it turns out that you can basically think of this infinite set as the following regular language over the alphabet of library interface variables. And the consequence of this is that our inference algorithm is actually going to have to infer infinite sets of path specifications. In particular, as I'll describe shortly, it's going to infer regular expressions over path specifications like the following. So now I'm going to talk about our inference algorithm. So just to give some very high-level intuition, our inference algorithm proceeds by constructing increasingly general sets of path specifications. So if you think of this blue oval as being the set of ground truth path specifications, basically it soundly models library code and it's as precise as possible, so it doesn't include any spurious path specifications. Then our inference algorithm is going to start off by constructing S0, which is a set of path specifications that are known to be precise. And then it's going to incrementally try to grow this set of path specifications. And at every step, it's going to try very hard to avoid overgeneralizing. So we can't guarantee it, but we're going to do a lot of work to make sure this doesn't happen. And the real reason we use this approach is really just because in practice, we found that it was relatively easy to start with a small set of path specifications and try to grow it. Trying to do the opposite is something we don't know how to do. So we don't know how to start with a sound set of path specifications and try to shrink it. So that's why we take this approach. So just to go into a little bit more detail, our algorithm is first going to generate a bunch of random candidate path specifications. And then it's going to basically synthesize unit tests to check for each candidate whether that candidate is precise. So whether that candidate is contained in the set S star. And it's only going to retain the candidates for which the unit tests pass. And just to say a little bit, the reason, and hopefully this will become a little bit more clear in a minute, but the reason path specifications are easy to infer is because we can actually synthesize, it's actually fairly straightforward to synthesize unit tests to check the precision of a path specification. And this is something we don't really know how to do if you give me an arbitrary specification in the form of, say, a code fragment. Okay, so this is going to be our set S0 constructed at the end of step 2. And then in step 3, we're going to inductively generalize S0 to a regular set of path specifications. So the first step is how to generate candidate specifications. And if you remember, a path specification is basically just a sequence of variables in the library interface. So we can really just use a sampling algorithm to generate these specifications. And you can use any sampling algorithm, for example, just randomly sample. But we also show that you can basically learn which variables are good to sample. For example, variables in collections classes are probably more likely to result in path specifications. So you can use a reinforcement learning algorithm known as Monte Carlo tree search to do sampling a little bit more intelligently. So the second step is the unit test synthesis. And I'm just going to describe this step via an example. So coming back to our original example for the box class. And recall that the semantics of this specification is that if the receiver of set and the receiver of get are aliased in the program, then the input, the parameter of set and the return value of get may be aliased as well. And basically what our unit test is going to do is it's going to construct a program a sequence of calls to set and get such that the receivers are aliased, and it's just going to check if the conclusion of this inference rule holds. So to do this, you need one call to set and one call to get. So to alias the receivers, we can just use the same variable. And of course, we have to initialize it. And we also have to initialize the parameter of set. And finally, we also have to have a variable that captures the output, the return value of get. And then we're just going to check if the parameter passed to set is aliased with the output, the return value of get. And if this test case passes, then we can actually guarantee that, that the candidate specification is precise. However, the converse is not true. So if the unit test returns false, then the unit test may return false even if the candidate specification is precise. And that's just because executions are inevitably under approximations of the library behavior. But we find that, and you can see our paper for some more detail, but we use a bunch of heuristics to make sure this works in practice. And finally, the third step of our algorithm is to generalize to a regular set. So we're going to start off with this set of positive examples, S0, from the previous step. And we're going to use a language learning algorithm to generalize this set of positive examples to a regular set of path specifications. And it's basically a learning algorithm based on RPNI. I'm not going to go into much detail, but basically what our algorithm does is, like RPNI, it constructs the prefix tree acceptor of the positive examples, and it tries to merge states in this finite state automaton. And whereas RPNI uses negative examples, our algorithm actually uses the unit tests generated in the first step to try to check when a merge is acceptable or not. And finally, our algorithm is going to output a regular set of path specifications. Yeah, and we also have a fourth step, which I didn't mention, which is just converting this. We can actually convert this regular set of path specifications into a set of code fragments that can be analyzed by our static PointsTo analysis. So finally, I'm just going to say a little bit about our evaluation. So in the paper, we have a more in-depth evaluation. But for this talk, I'm just going to focus on the part of our evaluation where we looked at the 12 most commonly used classes in the Java collections API. So things like map, list, vector, and so forth. And I'm going to show 3 different static PointsTo analyses. The first one is going to use the specifications inferred by our algorithm. The second one is going to use ground truth specifications. So these are basically specifications we wrote by hand. So they cover these 12 classes, and it's about 1,700 lines of code. And we also compare to analyzing the library implementation directly. So basically just using the bytecode provided in the Java SDK. So in addition to directly comparing the specifications, we're also going to compare the results of the PointsTo analysis. And basically, I'm going to use this metric R of S prime, which is it's basically the ratio of the number of PointsTo edges discovered by S over the number of PointsTo edges discovered by S prime. But we're going to ignore PointsTo edges that are kind of trivial, which we can discover even if we use empty specifications, which treats all of the library functions as no-ops. And we're going to just use make this comparison on a benchmark of 46 programs. So first, I'm going to compare the inferred versus the ground truth specifications. And basically, this measures how well we do compared to ground truth. So to do this comparison, we first looked at the specifications themselves. And we just restricted to the 50 most frequently used library functions. And on these 50 library functions, we had 100% precision and 97% recall. So recall was counted fractionally for technical reasons that I'm not going to get into. And we also compared using the PointsTo analysis. So here I've plotted for our 46 programs the metric R of inferred and true. And basically what this ratio shows is how many, the fraction of the ground truth PointsTo edges that were discovered using our inferred specifications. So because the ground truth is always kind of the best you can hope to do, everything here are false negatives in our algorithm. But on average, we did pretty well. Our false negative rate was only 24% on average. And for almost half the apps, we actually had a 0% false negative rate, which is pretty impressive. And so that was the first part of our evaluation. And the second part, we actually compared the implementation, analyzing the implementation to analyzing ground truth. And basically what this is trying to measure is how much worse does analyzing the implementation do compared to having all of the ground truth specifications. So it basically measures the value of specifications. And just to go through it quickly, so we measured the same ratio of the implementation to the ground truth. So everything above 1 is going to be a false positive PointsTo edge. So the average false positive rate was 62%, and the median was 115%. But at the very tail over here, we also found a couple of false negatives, in particular due to native code being used by the Java Collections API. So just to conclude, specifications are really a very promising way of addressing a lot of the problems with static analysis when analyzing large programs. And we firmly believe that specification inference can substantially improve the usability of static analysis tools in practice. So thank you for listening, and I'll be happy to take any questions.
Hello, interesting work. So I was wondering, what static analysis did you use for your experiments with static pointer analysis?
We used an Anderson, it's a flow-insensitive Anderson-style analysis that was context-sensitive.
Okay. And second question I had, was it a conscious decision to do a runtime-based approach? I mean, did you consider also inferring these specifications through static analysis?
It's very hard. I mean, if you try to infer them by statically analyzing the library code, you're going to run into all of the problems analyzing native code and everything. So that's why we used a dynamic approach, because you can execute this code, but it's really hard to analyze.
Thanks.
Hey, this is cool stuff.
Thank you.
I had a question. Like, you have a few collection classes in the library, and you said it was about 1,700 lines of code. Was that code, or was that manually written alias pads? Like, what exactly was that?
Right. So we actually implemented our specifications as code fragments for the ground truth. So yeah, that was code. Basically an implementation. Yeah, and it basically over-approximates the aliasing behavior of the library. So it's not like a valid implementation of the list class. It's just, it captures the aliasing behavior with respect to our PointsTo analysis.
Right. And I had one other question. So if we have like a small number of collections classes, like one could imagine an approach where you write specs for those, and then for the rest of the code, just do string matching and match up getters and setters. So do you have any idea of how well that approach would work versus doing the inference over all the data structures in the library?
I don't have a great sense of how that would work, but I think you would miss a lot of corner cases. There's kind of, yeah, you're right in that there are a lot of methods that have the same name, but we also found a long tail of kind of methods that like I've never seen before, that I've never used before, that hiding in the API that have really weird names that I think you would have trouble finding with a naive string matching approach.
Cool, thank you.
Hey, if you have a collection class and you put into it some object and then you need to get it back, is your specification powerful enough to actually compare the keys of what's put and what's get later?
No, so our PointsTo analysis collapses arrays into a single object, so it can't keep track of keys. And so you would need a more precise PointsTo analysis.
How did you specify the collections? You said you have ground truth specification. Is this just set one field?
Yeah.
Okay, thanks.
Okay, let's thank Osbert.